Hello and welcome to this presentation about the first data challenge. The assignment as understood by the group is enhancing and understanding the application of convolutional neural network models specifically designed for medical imaging to identify thoracic disorders from grayscale chest X-ray images. To this extent, it is important to develop a good model, but also evaluate its capabilities and consider how it can be implemented by practitioners, whilst also taking into account ethical considerations on every step. This description was based on the Canvas page, lectures, and background research such as interviews. For the main stakeholder, we have chosen the radiologist, and here the importance of explainability and ease of understanding is very high. To develop these objectives, we have already interviewed Dr. Erik van Schoon, a doctor that's heavily involved in AI research. We will take his opinion into account here. Other stakeholders include the patients and healthcare providers, as they have intertwining interests with the radiologist. We have, however, chosen to go with the radiologist as our main stakeholder because it gives us the most room to really improve the model to ease their workload and enable quicker processing of X-ray scans.
Moving into the research questions, we've identified three main areas of focus. The first one being the transparency and explainability of the model. More specifically, we want to find out how we can provide reasoning behind the decision-making process. Secondly, we want to optimize the model's accuracy and recall without compromising the explainability. A sub-question includes investigating the increase in complexity and how it impacts the trade-off between model accuracy and explainability. The last research question focuses on how the model's generalizability can be enhanced. It's important to note that in approaching each question, the ethical aspects will be explored in equal depth as the technical side. We then move on to the objectives related to the stakeholders, which have been identified following a conducted interview with Dr. Schoon and is involved with the use of AI in healthcare. We have further supplemented the interview findings with research into how radiologists worldwide implement AI to their advantage. The first point of explainability and transparency will allow practitioners to verify findings and make sure they're grounded in medical evidence that can be double-checked by the doctor. Secondly, regarding accuracy and recall, a model with low accuracy and recall will simply provide wrong diagnosis, and a model with high accuracy and recall that is unable to explain its findings will be unable to earn the trust of a practitioner. Making the model adept at handling complex or atypical data will increase its robustness and allow its use in a greater variety of cases. Technical aspects to be explored include feature importance analysis, model uncertainty quantification, increasing model complexity, data augmentation, and sampling strategies to increase robustness. Ethical aspects to be explored include considering the bias of our training data and how this can influence the model's findings, providing clear visual and/or textual feedback explaining the decision-making process, and providing suggestions in which cases the model can be used and what its limitations would be.
The dataset for this assignment consists of pre-processed chest X-ray images used to detect 5 common thoracic disorders plus a healthy case. It includes 16,841 training and 8,420 testing images with the labels, which represent conditions like pneumothorax, nodule, infiltration, and etc. Images were extracted from radiologic reports using NLP with an accuracy above 90%. All images are grayscaled and resized to 128 by 128 pixel size. Some of the images within the dataset contain meaningless information, what we consider noise, like medical equipment, cropped rotated images, or writing on images, which isn't always a bad thing. The object is to develop and refine a model that can accurately classify these images, taking into account the presence of noise and labeling inaccuracies, while also considering ethical implications of the automated diagnosis. To address the challenge of the dataset, including the varied quality and critical need for precise disease classification, we plan to implement additional data augmentation techniques alongside the data pre-processing techniques already applied to the provided dataset.
This CNN model identifies thoracic disorders from grayscale chest X-rays. It starts with an input layer for single-channeled images followed by convolutional blocks. These blocks include layers for feature detection, batch normalization, relu activation, pooling, and drop route to prevent overfitting. After refining features, data moves through fully connected layers for interpreting features and outputting diagnosis predictions. Training uses mini-batch gradient descent to minimize loss and improve accuracy. The evaluation is done by employing cross-entropy loss and calculation of the testing loss after training in each epoch. In line with our commitment to advancing medical imaging analysis, we propose the presented strategies to enhance models' performance. We aim to boost the model's feature extraction by incorporating convolutional layers with residual connections inspired by ResNet architectures. This is expected to improve accuracy in classifying thoracic disorders and enhance precision and recall metrics. It's crucial to note that increased convolutional layers may reduce explainability. Despite this, the use of residual connections has the potential to enable our network to efficiently handle more complex tasks. We will carefully balance model complexity with interpretability to ensure practicality. To increase the generalization ability of our model, we propose the implementation of data augmentation techniques. By expanding and diversifying our training dataset to random transformations, we aim to enhance our model's robustness and reduce overfitting. Rigorous evaluation of this approach will guide us in maximizing performance on unseen data. Continuous refinement of hyperparameters is essential for enhancing our model's performance. Through systematic experimentation with learning rates, batch sizes, and optimizer types, we intend to fine-tune the learning process. We aim to identify optimal settings for efficient learning and superior outcomes on validation dataset. In pursuit of enhanced explainability, we plan to implement heat maps to highlight image areas influencing the model's decisions. This visualization technique will provide valuable insights for medical practitioners, enabling them to better understand the model's reasoning process and its implications for diagnostic accuracy. A key element of our approach is to quantify the certainty of the model's predictions. By providing confidence measures for each prediction and outputting probabilities for multiple diagnoses, we aim to empower clinicians in decision-making processes. To evaluate our CNN model, we plan to use multiple metrics including accuracy, precision, recall, and F1 score to assess overall correctness and minimize false positives and negatives. Additionally, a confusion matrix will detail type 1 and type 2 errors, while the RRC curve and AUC will illustrate the model's diagnostic distinction capabilities. These metrics are chosen for their significance in evaluating medical diagnosis models' accuracy and reliability in clinical settings. For the model to actually bring ethical advantages to the medical field, it should work quickly, as losing time to a slow model is crucial when diagnosing a patient who needs timely treatment. Optimizing recall aligns with minimizing false negatives, as doing so enhances the model's ability to correctly identify conditions, minimizing the chances of missing potential cases. Explainability is important as it increases the model's trustworthiness, and without doctors' trust, the model is useless in their decision-making. Lastly, the risks of bias will be taken into account as we strive for fairness to all patients. Following the team's research presented in the previous slides, we've identified key areas to focus on and conduct experiments. As we enter the next phase of development, we've devised a strategic approach to enhance diagnostic capabilities, exploring the possibilities of the presented on the slide key areas. Our work plan divides these tasks among specialized sub-teams, with each sprint dedicated to a set of particular enhancements. In the upcoming Sprint 2, one sub-team will focus on the implementation of heat maps for visual interpretation and quantifying model certainty. Simultaneously, the other sub-team will concentrate on the described ways to enhance the model's performance. The aim is to produce significant results from the implementation by the end of Sprint 2, laying the groundwork for further improvements in Sprint 3. Additionally, the sprint will monitor and address potential ethical issues throughout the development process. This includes overseeing the impact of technical modifications on the project's ethical aspects and documenting any ethical concerns or consequences arising from experiments and technical changes. In conclusion, our project represents a comprehensive effort to not only improve a neural network model's accuracy, but also to ensure its effective use in medical diagnostics by professionals.